Hi everyone, welcome back to the Reading Club. This is an ongoing series where I read papers on mixed nature programming and discuss their key ideas in simple language. And in today's episode, I decided to deviate a little bit, and instead of discussing a paper, I will be discussing implementation details of pseudocost in SCIP. So I recently visited the ZIP campus, and I actually ended up working on a branching project that involved playing around with pseudocost. So I spent quite a lot of time understanding and manipulating SCIP's pseudocost implementation. And I feel that a lot of things that I saw in that code, they were not really published or taught in the classroom. Definitely not taught in the classroom. They might be published somewhere, but definitely not taught in the classroom. So hopefully, you'll also get to learn something new. And so let's get started. Okay, so let's start with the basic definition of pseudocost. Right, so the things that are actually taught in the classroom. So let's say we are at this node, and let's say when we solved the LP, we got the LP objective value as L0. And let's say the variable x was fractional, it was, let's say, 5.3. In one branch, we say that x is less than or equal to 5. Other branch, we say that x is greater or equal to 6. And over here, let's say on this branch, we observed this node, we solved LP again, and we saw that LP objective is L1. Right? So if you are minimizing, L1 is always going to be bigger than L0. And so if you want to maintain some sort of success statistic for x, that's a good statistic, how much we gain in the LP objective. So that is L1 minus L0. And we also want to normalize it for how much actually we moved in x, right? So this is actually divided by the fractional part in x, or how much we actually moved. So in this branch, it is we moved x by 0.3, and the other branch we moved x by 0.7. So in this branch, fx will be, let's say, 0.3, and in the other branch it will be 0.7, right? So per unit movement of x, how much gain in the LP objective we are observing, that's the statistic we are going to maintain, and that's basically pseudocost. Okay, so it's very simple, and this is like one data point, and we are going to branch on the same variable x again and again over many different parts of the our branch and boundary. So we are going to maintain an average of this, right? So that's basically the pseudocost, right? So the average average gain in the LP per unit movement of x, that's basically the pseudocost, right? So at some point of time, people said that variables behave differently when we branch on it in up direction and down direction. So we are going to maintain two different pseudocosts, right? So this is say down direction, and this is up direction. So we will maintain one average for up and one average for down. Two different averages will maintain. Okay, and so this maintaining of average is kind of not that hard. It's we just need to store the current average and the current count, how many updates we have added in this average, right? So if we have just these two, then it is very easy to keep adding new data points without actually storing all the individual data points, right? So we can just simply add new data points, basically compute this current sum by multiplying this average with count, and then add this data point and then divide by count plus 1, right? So that will be my new average. So either ways, we are now stuck into this two things, right? So there is up cost and up average and down average, right? So previously it was very simple, like if you want to choose one variable for branching, so if let's say if we have multiple variables which are fractional at this node, and if you want to choose one variable for branching, what we will do is we will measure which variable is expected to give me highest gain in the LP objective, right? So we'll look at their averages and their current fractionalities, and we'll compute that if we branch on X, we will gain this much on LP. If we branch on Y, we'll get this much on LP, and so on and so forth. And based on that, we'll select it, right? But now if we have two different averages, then how do we use them to compute a total score, like a single point score, which we can use for comparing different variables, right? So there are many different ways, right? So you can just simply add these two scores, right? So what is the average gain in up and what is the average gain in down, and just add them two and see what happens. There is another thing called take the minimum of these two. We can take the maximum of these two, and the one that actually works well is the product rule, right? So we basically multiply this up average with the down average, and one of them is 0, then we use this small number epsilon, because if let's say in one direction there is a huge gain and the other direction there is no gain, then sometimes we still want to consider that huge gain. So instead of multiplying it with 0, we are going to multiply it with the small number, which is epsilon. Right? So if that is 0, like if it is like smaller than epsilon. So that is the basics of pseudocost. Now let's figure out why exactly we want to learn pseudocost, right? So if we look at the best branching rules. So when I say branching, I basically mean variable selection, okay? Not node selection. We are only focusing on variable selection, right? So initially it was pseudocost at some point of time. Uh, it basically outperformed all those trivial branching rule that we had before, which is like basically branching on most fractional variables and random variables and all those things. So all of those were basically outperformed significantly by pseudocost, and it's been like quite a long time ago when pseudocost was invented, and it's been running around since then, so long. And in fact, the current best branching rules are just some like variations of pseudocost, right? So the current best one, we can say that is not exactly the best one, but the one that really outperforms pseudocost is reliable pseudocost. So I'm not going to discuss that in this video, what reliable pseudocost is. If you are taking that theory course in mixed integer programming, at some point of time, your instructor will teach you what reliable pseudocosts are. So I'm not going to do it. And the one that even outperforms the reliable pseudocost is basically hybrid branching. Hybrid branching. So obviously, like the unreliable pseudocost, the pseudocost is still like the major component of branching, and even in hybrid branching, which basically says that not just look at the pseudocost, but we'll also look at a bunch of other things. So first of all, pseudocost is obviously there, which is, let's say, reliable, but there are also other things like inference score. And then there is also conflict score, right? So those couple of things are basically added, and all of these scores are eventually merged to generate the final branching score. But still, the pseudocost is the major component that is driving this hybrid branching, right? So pseudocost has been important in the history, and it is still important. So this is, as of now, the state-of-the-art branching rule in SCIP. It is actually called reliable pseudocost, but technically it is hybrid branching because people didn't really modify people didn't really create a new branching rule for this. It's just that they ended up modifying this one and adding these other things to it. So this is the state of the art. It's still like it's called reliable pseudocost, but it is still like the pseudocost is still the major component of it. And the idea of pseudocost is not just limited to the MIP solvers, right? So I actually implemented the pseudocost in CP SAT solver as well. So there we don't even solve LP. Like even if we solve LP, we don't really need it. Like the pseudocost concept can be used even in the constraint programming setting, right? So the idea is that there is no fractional variables at all. Like everything in this is integer. So let's say no fractional. And in this CPSAT solver, it's in Google OR tools. The way we implemented it was basically we have literals for every this kind of bounds, right? So x is greater or equal to, it's one literal. And if you want to say that x is less than equal to t minus 1, we basically say that minus x is greater or equal to minus t minus 1. And this is my negated variable. And this is my positive variable. So we'll maintain pseudocost for positive variable, we'll maintain pseudocost for negative variable, and the rest of the details are same, right? So we say that the objective was this one, and at this node, and so let's say objective was O1, and when we branched on this variable, the objective we got was O2. So basically we are going to say O2 minus O1 and how much we moved that variable, right? So what was the lower bound for this variable, which is over here, it is T, and what was the lower bound at this node, whatever we observe at that point of time. Right, so and then again like LB change, right? So always I mean it's a kind of a choice. We can always either maintain the lower bounds or upper bound. It doesn't really matter. It's just that one way of discretizing things and creating this SAT friendly variables, literals for that. So this is like something that we can maintain even in the CP setting, and then use this data for selecting branching variable. And sometimes it turns out that this branching strategy turns out to be beneficial for certain types of problems, right? So Again, over here also it is basically combine the two scores for positive and negative variables when we want to pick some variable for branching by product rule. Right, so we take the average for this positive variable, take the average for this negative variable, combine those two averages by taking the product, and we continue with the variable selection like that. Okay, so now we are going to discuss some specific issues with the implementation that I just described, right? So what happens, what if LP is not solved at a node, right? So what do we do in this kind of scenario? So let me explain why I'm going to discuss this. First of all, let's say we have this node. Let's say we branched on X. We had our LP objective L1, and over here we reached over here, and we, for some reason at this node, we could not solve LP, right? So we, let's say, hit some numerical issues, and we just simply could not solve LP, or the LP solution that we observed was uh, facing basically like bound related issues and everything. So long story short, there are many reasons why the LP was not solved properly at this node. And so at this, and this kind of scenarios, what MIP solvers do is they don't give up, they don't crash, they simply just say that let's branch on this node again, and eventually this LP error, the numerical error that we are observing, will go away, right? So we branch on, let's say, another variable y over here using the LP solution of this node, right? So let's say this is the node where LP is solved, and this is the node where LP is not solved, but we are basically using the solution value of this LP, but for a different variable y, and we are going to branch on this variable y. Okay. And so let's say we reach this node, and let's say for some magical reason the LP error was gone, and the LP objective for this node, let's say we got the L3, right? So there is L1, there is L3, there is no L2 because we could not solve LP over here. So in this kind of scenario, how do we basically do these pseudo cost updates, right? So previously it was easy that we wanted, when we were at this node, we solved the LP again and we updated the pseudo cost for X and we were happy. And now over here, there is an in-between Y node. There is no L2, there is directly L3. So what do we do about pseudo cost update, right? So the gain in the LP objective is obviously L3 minus L1, but what do we divide it with? Should it be X, fractionality of X? Should it be fractionality of Y? What do we do? So turns out that we can actually update the pseudo cost of both of this. So the way it is done in SCIP is this way. So they basically say that X is moved by Fx, and we are going to update pseudo cost for Fx, which is fine. And we are also going to update pseudo cost for Y. So L3 minus L1 divided by Fy. Now both of them were actually responsible for this gain, because the value of Y was chosen based on the LP solution over here. So we could have basically switched these two variables, and we still would have received hopefully the same LP objective L3, regardless of whether we branch on X first or Y first. But let's say that assumption may not be true all the time, but let's say it is true. In that case, we are also going to give some credit to Y, right? So in fact, we are going to give both of them equal credits, and we are going to maintain update the pseudo cost for both of them. But let's say what happens is, let's say this one is, let's say 6.2, and let's say the current average for X is let's say 7.3 average, right? And the count was, let's say, 5. So normally what we will do is that I'll just say that 7.3 times 5 plus 6.2 divided by what? No, the new count is 6 basically, right? So this would have been my normally new pseudo cost average. This would basically replace this, but we are going to basically distribute the gains equally in these two variables, right? So instead of doing this way, what we are going to do is that we are going to increase the count by half. So instead of it will be 5 plus 1 6, it will be 5 plus half. It is 5.5. The new count will be 5.5. So I'll say that this 6.2 is only half a update, not a full update for pseudo cost. So I'm going to multiply this by 0.5, and instead of 6, I'm going to say that it will be 5 plus 0.5, so 5.5, the new total average, right? So this will be for X, and similarly for Y it will be another update, right? So both of them we are doing the down averages, we are modifying, and so this is how we are going to modify both of them. Okay, so if this would have continued, let's say even at this node we failed to solve LP, then and we branched on some variable Z, so we'll distribute the gains at the next node where we solve LP to all these three variables X, Y, and Z, one third, one third, one third, right? So the counts will be increased by not one, not half, it will be one third. So previously this count used to be an integer, but now it is a fractional number, it's a real number. Right? So count is, if you notice in the SCIP implementation of SCIP variable history, the count is actually a real number and not an integer. Whereas in a lot of different solvers, especially the one in CPSAT that I mentioned, it is integer, because there is no such thing, like we don't face this kind of issues there. Even in hikes, as of now, from what I observed last time, it is still, count is still integer and they are updated +1, and this kind of scenarios is basically not I couldn't see this kind of scenarios happening and how they are being updated and all those things, right? So this is one of the kind of tiny details that is needed to understand how these MIP solvers behave when things go wrong. And so similarly, the other thing I actually learned while looking at the SCIP code was this concept of valid pseudo cost updates. So let's try to understand what this is and why this is needed. Again, this is like only something that is I saw only in SCIP. In hikes, I don't think I saw this kind of things. But again, like I didn't really observe a lot of hikes code, so I might be wrong. Okay, so let's say we are here at X and let's say the gain over here was L1, and we branched, we reach here, no LP related issues. The gain over here is L2, and over here the X was, let's say, 5.3, of course, and we branch and say that X is less than equal to 5, right? And over here, normally what we would have done is that L2 minus L1 divided by 0.3, right? So first of all, this is wrong, right? So this is not correct, because 0.3 is not the right thing to divide with. X could have moved by more than 0.3, right? So here X could have been like X equal to, let's say, 3.2 when we solve this LP again. And so here, instead of dividing it by just 0.3, it is just simply not fair, because X actually moved by a lot more than 0.3, right? So we should be dividing it by that number if at all we are doing the pseudo cost update. So it's not just fx, the fractional part of x, it's actually how much actually x moved in the two LPs, right? So this is actually there in all solvers. That's there is nothing new about it. It's just that sometimes when people teach theory, they use this fx, and it is kind of not correct. The fx is not the right thing to divide. It's the actual solve delta people use. That's what people use, right? So that's what I described we use in CPSAT, and it's also there in hikes as well, and SCIP as well. But that's not the concept of valid pseudo cost update. What I'm trying to get to is, let's say, over here the bound of x we maintain, right? So the one that we decided was 5, upper bound was 5, and here the upper bound for x is 3.2. so this might even happen, like, so when we say that x is less than equal to 5, and some bound propagation might happen at this node, and say that, you know, if x is less than equal to 5, then it doesn't really make sense for x to take values greater than 4, so x is effectively less than equal to 4. This is implied by x is less than equal to 5. That can happen, right? So it can happen via a couple of other variables as well. And so even in this case, x is actually taking the value 3.2. And so the definition of valid pseudo cost update in SCIP is that the new value, in fact, first of all, the old value, which is 5.3, that should be violated by the new bound, which is x is less than equal to 4, which is definitely valid. So that part is checked. So if that is not happening, then there is something wrong, and the pseudo cost update is not valid. The other part is that the new LP solution value, which is 3.2, it should be at this bound. So it should be tight at this bound. So x should be equal to 4. If x is not equal to 4, if it is not at this bound, then it was not the x movement that really caused the improvement in the objective. It was something else, totally something else. And so in those kind of scenarios, when if x is not equal to its new bound, SCIP apparently discards this entire pseudo cost update as well. So it is no longer valid pseudo cost update. And that's the idea, is that if we are observing if we are giving some reward to x, then this bound change, the LP objective gain, should be because of the bound change in x and nothing else, right? So that is no longer true when x is taking this kind of value, which is way inside the bound, right? So that in that case, the pseudo cost update is not valid, and SCIP basically does not SCIP simply just discard that update, right? So it just moves on. And that way, like the definition of pseudo cost is slightly different from what is described in theory all the time, right? So valid pseudo cost updates. So in fact, it may even happen that if you compare nothing but the pseudo cost branching rule in SCIP and hikes, you will still observe different performances, because pseudo cost means something entirely different in SCIP, whereas it means something different in hikes because of this validity rule. Okay, so we are almost at the end, and there are still a couple of tiny details that I didn't really describe because they're like just too tiny. So I'm not really going to describe. So let me summarize what we saw today. So we saw what pseudo costs are, basically the simple definition, right? And we also saw that pseudo cost can actually be used in other solvers, right? So I actually described how basically pseudo cost is used in CPSAT. So I was actually involved in this implementation, pseudo cost implementation in CPSAT and Google tools. But pseudo cost is actually even used inside SCIP in a different context as well, right? So SCIP is actually even a non-linear solver. So it actually solves non-linear MIPS, so MINLPs, right? So non-linear setting. Right, so I actually got too scared of looking at how pseudo costs behave in this setting, and so in fact there are also they basically maintain pseudo cost even for continuous variables, and that piece of code of maintaining pseudo cost and updating pseudo cost for continuous variables. It's way larger than the pseudo cost updates for regular integer variables for MILPs. Right, so I don't really know enough theory about nonlinear programming, MINLP and non-convex kind of things. So I am not really going to describe it. At SCIP, I think I talked to Senia once, and she actually could understand how the pseudo costs are updated in continuous variables. So if you are at SCIP and if you ever get to meet Senia, just ask her how these things are working. But yeah, I couldn't really spend time on this because I had limited time at SCIP, and I didn't really want to spend much time learning nonlinear programming at that point of time. Right, so a couple of other things we learned was that what do we do when LP is not solved, right? So how do we maintain the pseudo cost updates and this, and what is valid pseudo cost update? So these are like the tiny little things that that basically makes the overall code super complex to read, and especially these two things are definitely not taught in any classrooms, and any places that I've learned pseudocost. These two things are definitely not taught. This one can be taught definitely in the classroom settings, but these things are, so this basically kind of it will show you that there is a big gap between what we learn in theory and how actually things are implemented in solvers, right? So there are tiny little things you can only appreciate when you actually work on solvers, because you'll never face this issue of LP not being solved in theory, right? Because nobody really, this even very rarely happens in practice as well. So nobody really spends a lot of time figuring out what to do in this kind of scenario, or why this valid pseudo cost updates are needed. Like, at some point of time, SCIP developers figured out that pseudo cost updates otherwise can be noisy, and so we need to have this valid pseudo cost update as a filter for updating pseudo cost, and that resulted in some benefits, but I don't think I saw this thing in regular textbooks for when we are taught pseudocost, right? So these are like the tiny things that you should keep in mind, that even the basic theoretical idea, pseudocost, the basic theoretical idea is very simple, right? It's a one line explanation that per unit. So what is the LP objective gain per unit movement in the variables? All right, so that's pseudocost. It's a one line description, and it overall, if you look at the code, it's so complex and it is just mind boggling, right? So yeah. So I also actually got a chance to work on pseudocost, one project on and SCIP related to pseudocost, and I will be talking about it in this year's ISMP 2024. That's actually happening in Montreal. If you are here, come and meet me, and probably if you are attending the ISMP, then yeah, come to my talk and see what I worked on, right? So I basically worked on a variation of pseudocost, which apparently improved the benchmark, which apparently improved the current state-of-the-art branching rule on SCIP and will be added in the SCIP code. So I'll be talking about that in the ISMP, and hope to see you there, and hope that you learned something new. And if you are new here, please don't forget to like and make sure you subscribe to keep getting notifications for my upcoming videos. That's all. Thank you. Bye.